A crow drops a walnut into traffic and waits. The shell skids across the asphalt. One car misses it. Another clips it. A bus roars past hard enough to shake the curb. The crow does not flinch. It watches lanes, wheels, lights, people, timing. Then the signal changes. It steps into the crosswalk, picks the walnut clean, and gets back to the sidewalk before the engines move again. That should be impossible, because somewhere inside that tiny head, the bird has learned the rules of a machine it did not evolve to understand. And once you see that, the problem gets bigger. A wild animal has learned that cars can crack what its beak cannot. It has learned that traffic lights change behavior. It has learned that a human street contains safe moments hidden inside it. So how smart are birds really? For a long time, the answer seemed obvious. Not very. Birds were supposed to be instinct with feathers, tiny brains, tiny lives. Peck here, sing there, fly south when it gets cold. If you wanted serious intelligence, you looked at apes, dolphins, elephants. Birds looked automatic, and their brains seemed to support that idea. Mammals have a neocortex, the wrinkled outer layer linked to planning, inhibition, and flexible behavior. Birds do not. Their brains are small, smooth, and built on a different plan. So the old conclusion sounded clean. No cortex, no higher thought. Then birds started making that conclusion look stupid. The crows in Japan are a perfect example, because nobody trained them. These were wild city crows dropping hard walnuts onto roads, letting cars do the cracking, and often choosing intersections where traffic patterns gave them a safer chance to collect the food. Look at what that demands. First, the bird has to grasp that a moving machine can do useful physical work. Then it has to place the walnut where that force will hit it. Then it has to wait instead of rushing in too early. Then it has to move at the moment the street becomes safe. If a chimpanzee did that with a rock, almost everyone would call it intelligence immediately. And that is where the real story begins, because this is not just about clever crows. It is about something stranger. For decades, scientists assumed that if intelligence became complex enough, it had to look something like ours on the inside. Birds quietly demolished that idea. They plan, they improvise, they remember specific past events. And they are doing it with a brain architecture that is not a stripped-down mammal version. It is another design, a separate solution. That is why birds feel eerie. A chimpanzee looks close enough to us that intelligence almost feels expected. It has hands. Expressions we recognize. A crow feels different. Beak, black eyes, quick mechanical movements. It looks simple right up until the moment it solves a problem that should have stopped it cold. Take tool use. One of the most famous examples comes from New Caledonian crows, black birds from a Pacific island that make tools in the wild. They trim twigs. They shape plant material. They select some materials over others. In some populations, the designs are so consistent they look less like random improvisation and more like local tradition. That alone was bad enough for the old view. Then came Betty. Betty was a New Caledonian crow in a lab experiment. Researchers placed a small bucket of food at the bottom of a vertical tube. She could not reach it with her beak. Nearby was a piece of wire. Betty bent the wire into a hook and lifted the bucket out. The clip spread because it did not feel like reflex. It felt like invention. A problem appears. The right tool is missing. The bird makes one. Later, researchers argued over the details. Maybe the act was shaped by natural crow behavior more than people first realized. Maybe the miracle had been overstated. But the debate was no longer about whether a bird could solve a novel physical problem. The debate was about what mental machinery it used. That is a very different conversation. And once that conversation started, it spread. Because birds were not showing one weird talent. They were showing different talents in different places, as if intelligence had been rebuilt in pieces across multiple lineages. Some of the strongest evidence came from social life. Imagine you are a raven hiding food. You wedge meat into a crevice, cover it, step back. Another raven has been watching from a branch above. Suddenly the problem is different. Now the danger is not hunger. It is knowledge. Somebody else saw where the food went. Ravens respond to that. Researchers found that ravens often re-hide cached food if another bird witnessed the original hiding place. More revealing still, ravens with experience stealing from others became especially cautious when protecting their own caches. That detail matters. A bird that has stolen before behaves as if it understands what a thief can do. It uses its own past behavior to predict another bird's future behavior. Scientists are careful here, and they should be. Humans are very good at projecting little human dramas onto animals. But this much is hard to escape. The raven is not reacting to motion the way it would react to wind or noise. It is treating another bird like a mind, a rival that has seen something, a rival that can use that information later. Then birds attacked memory. Scrub jays hide food in many places and recover it later. But what they remember is more specific than a simple mental map. In experiments, scrub jays kept track of what they had stored, where they had stored it, and how much time had passed. That matters because some foods spoil quickly while others last. If worms have had time to rot, the bird shifts toward the cache that should still be edible. Psychologists call this episodic-like memory. The phrase is cautious because nobody wants to casually declare that a jay remembers the past exactly the way a human does. The behavior itself is less cautious. The bird is tracking the what, where, and when of a previous event, then using that memory to make a better decision now. And then the jays did something even more disruptive. They planned ahead. In one experiment, the birds spent mornings in compartments where breakfast appeared in one place but not another. Later, when given food to cache, they stored more in the compartment where food would be absent the next morning. For a long time, flexible planning for the future was treated as one of the safest dividing lines between humans and other animals. Then a scrub jay started packing breakfast for its future self. By this point, the old hierarchy was already in trouble. Then another fact makes everything feel even less stable. These minds belong to the only dinosaurs still alive. Every crow on a telephone wire, every pigeon under a bench, every raven on a highway sign comes from the branch of dinosaurs that survived the asteroid and kept going, which means some of the most flexible non-human minds we know are sitting inside dinosaur skulls the size of a lime. Parrots show the same thing from another angle. People often dismiss parrots by saying they are just mimicking, as if mimicry were trivial. It is not. Vocal learning is demanding. An animal has to hear a sound, store it, control its vocal apparatus with precision, and reproduce that sound in a useful context. The most famous parrot in cognition research was Alex, an African gray studied by Irene Pepperberg. Alex could label colors, shapes, materials, and quantities. He answered questions about which object was blue or which key was made of wood. He understood same and different. He counted small numbers reliably. Of course there was skepticism. There should have been. A talking bird can feel more human than it really is, but the fact that researchers had to argue over how much Alex understood says something important. Nobody was stuck on whether a bird could do anything language-like. The serious argument was where the limits were. Again, the border moved. So what changed? Partly, scientists stopped asking the wrong question. For years, the hidden assumption was that intelligence required a mammal-style brain, especially a neocortex. Since birds lacked one, whatever clever behavior they showed had to be downgraded somehow. Instinct, association, fancy reflex, anything but thought. Then neurobiology started catching up to behavior. Bird brains are small, yes. But small does not mean crude, and smooth does not mean simple. Their brains are organized differently, yet some regions perform functions similar to those handled by mammalian cortical areas. More than that, many bird brains pack neurons with extraordinary density. In parrots and songbirds especially, neurons are packed into the forebrain far more tightly than in many mammals. So a bird brain can be tiny and still deliver serious computing power. Corvids and parrots, in particular, have forebrain neuron counts that rival or exceed those of some primates. Not because their brains are larger, because they are built differently, more compressed, more efficient. This is the flip in the story. Bird intelligence is not surprising because birds turned out to be little feathered primates after all. Bird intelligence is surprising because they did not. Evolution built a different kind of brain and still arrived at planning, problem-solving, social strategy, innovation, and memory that look uncomfortably familiar from the outside. That is the real revelation. For decades, scientists assumed intelligence needed a mammal brain. Then birds quietly demolished that idea. Evolution had invented another solution. Once you see it that way, all the scattered examples stop being a list and start becoming evidence for one larger claim. The crow in traffic, the raven protecting a cache, the jay preparing breakfast, the parrot using learned symbols. These are not isolated party tricks. They are glimpses of a second route to complex cognition. Why would evolution do this twice? Because intelligence pays when life gets complicated enough. Food is hard. Sometimes it is hidden, sealed, seasonal, or easy to steal. Social life is hard. Rivals watch. Alliances matter. Young animals need to learn quickly. Birds face those pressures under a different set of constraints than we did. They do not have hands. Many of them fly, and flight makes weight expensive. Evolution could not just keep enlarging their heads forever, so their intelligence had to become compact, dense, efficient. That is one reason it feels so uncanny. We are used to associating intelligence with size, with grasping hands, with faces that resemble our own. Birds offer almost none of that visual comfort. They look light, fast, decorative even. Then one of them solves a problem with timing, restraint, and foresight, and suddenly the whole ranking system starts shaking. Because intelligence was never a contest to become human. Humans build cities, write laws, launch satellites, and make documentaries about birds. Birds do not, but that is not the standard that matters here. The interesting question is what intelligence looks like when it evolves along another path entirely. What does a mind look like with no hands, no cortex, and no reason to invent mathematics, but every reason to master the problems of a bird's life? It looks like a raven moving its food because another raven was watching. It looks like a parrot deploying the right learned sound at the right moment. And it looks like a crow using a traffic system as a tool. That is why the phrase bird brain aged so badly. It assumes intelligence must either resemble ours or barely count at all. It sees feathers, flight, and a skull the size of a walnut, and expects a simple machine inside. But birds are not tiny automatons running a fixed script. They are minds. Small, strange yet efficient minds. Minds built along a route evolution took completely apart from ours, and yet somehow capable of arriving at many of the same destinations, which means the birds people ignore every day are not background scenery. The pigeons under the bench are solving problems. The raven above the parking lot is tracking who is watching whom, and the crow at the curb is waiting for the light.